to the last topic that we discussed, that was about, let's call anelasticity, so some rheology, some viscoelastic modeling, some application to the definition of Q, but now we understand it's called quality factor. You can find it in many places, from EM waves or electronic circuits to the Earth. So then we discovered this factor that is letting us to explain one of the factors that are affecting wave amplitudes. Please remember also geometrical spreading, that is one of the main factors affecting the decay of amplitude with distance. Of course, that's physics, basic physics, conservation of energy. Then anelasticity, there is an additional feature that we can call scattering, that is a sort of the approach to the diffusion of a seismic wave field. But the main topic was anelasticity. Going back to your homework, some of you have been writing to me this morning, but the solution is relatively simple. Okay, let me share my screen. Relatively simple. Okay, I'm screen sharing. So this is page 192 of the Seismology section textbook. You see, previously there are some definitions. You should recognize something here. The damped oscillator. We consider also the forced oscillator that will reappear in a new fashion in the last lecture when we're going to speak about the response spectra. Okay, you should recognize this factor here because we discussed it. It's Q, relaxation time, everything is nice here, and then here you got the solution. Because you can, from the damped oscillator, you can get the definition of attenuation, Q minus 1, and here there is the definition of beta with complex as a complex velocity, and of course the imaginary part is taking care about what we can call the phase attenuation. Q beta, Q alpha, K is the bulk modulus, and then with an approximation here, you find your answer. So I did your homework. Nice. So the answer is here. Okay? And the approximation to obtain that let's say simple version of the formula is here. General little energy is lost in compression, Qk is small, and so Q alpha is 9/4 Q beta. Well done. Okay. Have I answered to you? So the answer is at page 192. And as you can see, it's containing previously what we had been discussing, part of what we have been discussing during the last lecture. This is the Q constant, the definition of Q as a decay factor, spatial Q, time Q, and let's see, okay, the bi-peak, and that's it. And this is the dispersion due to causality when Q is constant. So welcome home, that's Azimi's law. So no tricks in the last lecture, you can find some support material here, as you can see. Here, it's the story about the viscoelastic modeling, it's a little bit shorter. Please remember what is an SLS, so standard linear solid. Okay, and that's it. Oh, I'm sorry. Please let me sorry, because I have a commission. Let me answer my phone just for 1 second, and I'm going to mute my, okay, sorry. Sì, pronto? Sì, chi parla? Allora, buongiorno, possiamo sentirci dopo, sto facendo lezione, grazie. Vi richiedo io, grazie. Sorry guys, but it's a messy day. I'm very sorry for this. But since I'm waiting some important calls,
no problem.
And this was an unknown number, but okay.
No. I want to learn Italian. I like the language.
Okay. So what I was saying, that I was, how to say, trying to make lectures, if we can discuss later. It was not a commercial call, but it was something related to energy here. And okay, so it was not commercial. But so I was saying, can we call back later? Possiamo sentirci dopo. Okay, that's the Italian fashion. I was relatively polite, okay? So it was a polite answer. Okay, let me switch off. If an important call is coming, I will find it. Okay, I switch it off. Okay, so now let's speak about this. My screen is still in sharing, I hope. That's the title. And I've put here many pictures and movies. I hope they are going to work. I tried to update them also yesterday. There are actually a couple of formulas. The only formula that, how to say, the slide with the expression is this one. Actually, it's not what I'm using to model tsunamis, but it's the only page with formulas here. So compared to the other lectures, it should be a little bit more relaxing. Now let me start as I was doing during the course at the beginning, especially at the beginning of the course. I was using the results and data collected after the Toku event of March 2011 to show how some beautiful messages in that tragic earthquake appeared. For example, if you remember, during the first lecture, I was showing to you how the rupture appeared on the records on the coastline. So it complicated the rupture, how GPS signals were revealing some permanent displacement. That's the near field. Some acceleration time series were revealing how the rupture could be complex, and some of them will reappear in the last lecture on Friday, when we will speak a little bit about hazard and seismic input to buildings. Some of them were showing the duration of the motion, seismic motion. But let me use another couple of recordings here to make a bridge towards something totally different, as I was telling you. So let's start. Now, what do we have here? Well, these are two recordings collected here, where there are some pressure gauges put at the ocean bottom. You see the red star of the main shock. We know now that it can be called epicenter or hypocenter, but the rupture was much more complicated than a point. Now we know we can put the focal mechanism, whatever. But now let's give a look to the pressure gauges. Now the pressure gauges can record on the ocean bottom, of course, seismic waves. If you want, they are more coupled to the P wave part of the wave field. And it appears here. You see, it's very nice. These wiggles here are appearing there, but then we have something that is beginning as a very slow raising and slow arriving, because it's arriving much later here, with a frequency content that is totally different than these ones. Okay, and this is due to the perturbation that is traveling as a gravity wave, and we can call it tsunami wave, in the fluid part of the Earth. Here we have a sort of a trench, so it could be very deep at that part. And these depths here, we may have 1,000 of as a bathymetry, so it could be a huge amount of water. And it's moving. It's moving with this long period motion, and it's impressive in terms of amplitude here. Slow, it's reaching the peak. If you look at the minutes here, it's taking 20 minutes to increase. So something is arriving that is long period, and let's remember this. And so you look at this signal here compared to these wiggles here that are the P, mainly the P waves. So long period, slow, but with something that has a huge amplitude, at least in the water part. So this is the tsunami. And what we're going to discuss now is how an earthquake can generate tsunami, but actually it's a gravity wave. And we will try to look also some very basic physics here on one side. Then we will try to couple this very basic physics with some fluid dynamics in a very simple way that you have been studying in other courses. Definitely for you diploma guys and girls, you studied it during other courses for maybe many, and with a much better formalism than today. But we will see how these gravity waves can assume long period, relatively slow, relatively compared to what? To seismic waves, and they could be very impressive. So they are also related to the concept of hazard. Okay, let's move how to collect usually a tsunami signal. So this is a theoretical seismology course, but we spent, let's say, 1 hour in discussing seismic instruments, also because they were a bridge to the definition of instrumental seismology, was one of the factors leading to the definition of magnitude and to understand the physics of a source. Let's spend 1 minute about the instruments that can record a tsunami. Now, what about traditionally, before essentially the Sumatra earthquake, the instruments that could record tsunamis, actually they were mariograms or tide gauges, something that was related to measure the fluid motion at very long periods, or like tides, of course, or something that could measure the water level when there is another gravity wave. It could be a wind wave. But nowadays, the best instrumental station to record tsunamis is made by what is called a dart buoy. They are not so common. They were not so common. They were deployed in the Pacific, but now they are in the ocean, Indian Ocean, pardon. There are some now. There are many in the Mediterranean. So the tsunami warning systems now, they are using it. Well, actually, how it's made, this station. Okay, we have a pressure gauge, for example, here that could record seismic waves at the same time. So bottom pressure recorder, but also, of course, so the perturbation carried by seismic waves, and then the perturbation carried by the change of the water level there. But what is more important is that now we have a GPS here on a buoy, and this system can transmit messages or its information usually to satellites. So we have a different measure both on the surface and on the bottom of this perturbation carried by these giant gravity waves. And for example, you can see here this GPS buoy. This is one of the system that was collecting data during the Toku event, and this is what has been recorded in Kamaishi, and this is very impressive. Look at the very long period here. These are days, hours, I'm sorry. So it's very long period. Please remember, after the video, the movie that we have been looking at, some animations that we had been looking during the first lecture, that the wave passage, the seismic wave passage on the Japanese islands was lasting, and it was a long-lasting signal, let's say up to 6 minutes. But here we have hours, as you can see. This wiggles, okay, there are some short period, relatively short period wiggles here. But if you look at this period, it's very long and very impressive in meters. Now, can we understand this? This is what we will try to do. So you see a typical tsunami waveform, very different from a seismic waveform. We can see here a sort of a inside vision of the first arrival. You see this gradual rise, then a rapid rise here. But look at the time. These are 20 minutes, so it's very long. Waves are traveling, seismic waves now are traveling through the world. The best with Japan in some minutes, you know that in 90 minutes they are going to travel the Earth. And so here tsunamis are arriving to the Japanese coast. So they are relatively slow. Why? Because they're gravity waves and not seismic waves. And this, I left this because Kenji Satake, that is one of the big names dealing with seismology and tsunami, well, he modeled, you see here a sketch, a cartoon of what was occurring in the subduction between the Pacific plate, and he was modeling some similar features of what occurred also in the past. You know that the Japanese seismic history is rich of very important events, and the names of these events usually are associated to how in Japan they measure the years. So in eras, and so for example, there is the Jogan period, the Meiji, Sanriku, the Meiji period, the Showa period. So these names here are referring to earthquakes that occurred in the past, like 1896, 1933. And actually, also if the tsunami of March 2011 was a sort of a surprise, well, actually, it should not, because in the past, similar events occurred on the Japanese coast. And we will see this also at the end of the lecture. Okay, starting from the collection of heights collected along the Japanese coast, the collective image that in the days after that event, for example, here you see this sketch that has been plotted just a couple of days. Let's say that they are impressive. They are impressive because in some places the height, and you see in the next picture what is a tsunami height or what is called tsunami run-up, they are impressive. And if you have been looking at the news and the media at that time, it's plenty of very impressive videos of tsunami waves reaching the coast. Okay, now just as a sort of a relatively simple terminology here, what do we have here? Actually, what we call tsunami height is a measure that is done, let's say, in open sea or open ocean. So it's the height of a wave referred to the average, maybe filtered by tides, stuff like that, of the average level of the sea. Then when you have not interference, but let's say when the gravity wave is entering into the land, its entrance will depend, of course, on the local bathymetry. Maybe the coast could be very steep, or it could be very gentle. According to this interaction between the waves, the fluid waves, the gravity waves, and the local bathymetry, you can have a different interaction. And so the final height conquered inland could be very different. Of course, this depends also on the local, mainly by the local bathymetry, and the conditions here, we can call that in open sea. So the maximum height reached at the penetration depth here, that's called run-up. So when you hear the run-up, you have to think that there is not the pure height of the wave, but the height reached by the wave when they are after their incoming into the land. And that depends, of course, if you have defenses, if you have steep barriers there, or if you don't. So you may have a smaller run-up, but a very big penetration depth. So the key word for this slide here is wave height, and tsunami run-up. And if you look at what has been collected in those days as tsunami height, some values are really impressive here. And you see here, okay, I'm not convinced, I cannot read Japanese, but I'm not convinced that all of these heights here are tsunami heights, because this was what has been reported in the caption, but in my opinion, it was tsunami run-up. By the way, in any case, the red dots that have been measured after the 2011 event, they are impressive in some points, tens of meters. Well, but they are comparable with some values that have been recorded also after the Showa and the Meiji events, 1933, 1896 here, because in some part of the coast, similar heights have been reached. This is for the northern Sanriku region of Japan. And here there are some values that are impressive as well, also if a little bit lower in the other provinces here, in the southern part of the Sanriku. So the message that we can get from the signatures of the tsunami waves reaching the Japanese coast after that mega earthquake was an impressive message. And after that event, many modelers, and there are some really impressive modelers in the Japanese institutes, tried to reproduce what occurred there. So we have seen the animations of the motion recorded and simulated. We have seen simulations of the rupture, with also the message that the rupture was lasting maybe 2 minutes. So it was a complicated and beautiful kinematic process there. Now, what about the tsunami excitation? Well, the key word, the message, one of the most important messages that I want to leave to you today is that tsunami waves, and I've sketched this statement later, are long period gravity waves. And long period, such a long period, we can say as an order of magnitude, let's say 1,000 seconds. It's a very long period. Also, if coupled with a relatively low velocity, let me try to trust my fate here, and let me write one expression that is maybe one of the most important ones for tsunami. It's very simple. Sorry, I have to collect my pen. And okay. One of the simplest expressions, but useful for tsunami velocity, is the square root of g, the gravity acceleration, times the height of the fluid. What does it mean? That on average, the velocity of a tsunami, that is a gravity wave, in this condition, it's called deep water condition, we will see later why it's called like that, reaches, for an average ocean of 4,000 meters, the velocity of 200 meters. So 0.2 kilometers per second. Okay, it's fast, but it's not that fast compared to the seismic waves. By the way, if you multiply this velocity for 1,000 seconds, you get a very large wavelength of the order of thousands of kilometers, or hundreds of kilometers, or tens of kilometers. So their average wavelength is very large. What does it mean? That the resolving power of those waves in generation propagation is large. And so when you see this animation, for example, you see that the blues and reds that are describing the wave propagation, they are large, as you can see. You can imagine to see a peak, a valley, so crests and valleys here, but you see they are large. This is one of the most important features of tsunami waves. So let me expand. You see the double propagation, one towards the Japanese coast, then you're reaching the local bathymetry there, and then we have an animation that is pointing towards the open ocean, and it's going to propagate to the other side of the ocean. So long periods, relatively low velocities compared to the seismic waves, but large wavelengths and larger propagation times. These waves took about 40 minutes, between 20 and 40 minutes to reach the Japanese coast. And well, the message here, it's long time. Well, it's not long if you have to prepare for an evacuation, if you trust it. So in terms of hazard, 20 minutes could be a long time because you can start some procedures. Could be a short time if you're not prepared, of course. And maybe the Japanese social tissue that is one of the most and best prepared to this hazard, actually they undervaluated it. So they were so used to tsunami warnings for a magnitude 8 event that they were carrying, of course, they are Japanese, to the warning, but they were a little bit relaxed. So everything was ready for rescue, for other things. Barriers were there, and you will see them. But what maybe just a few persons forecasted was a magnitude 9. And 9 means that the amplitude of the waves reaching the coast was pretty much the double as weighted for a magnitude 8. Defenses, and that's the last part of the lecture, were not working, well, not as they were supposed to. And also the rescue procedures were a little bit undervaluated. That's why a large hazard had been causing the tragic consequences that we have seen. But okay, let's stay on the physics side. Let's give a look to the simulations that Kenji Satake did, let's say in the next days after the event, compared to some available data. And you see here a comparison between the modeling and the recording, just a few of them, because most of the instruments had been wiped out because the coastal instruments were not dart buoys. Some tsunami meters were there, but the amplitude was so large in some places that they had been wiped out. But in the next page, you will see a more complete vision after that has been collected a few days after the event, so let's say within 1 month. But what you can appreciate here, that in some places here, for example, the Kamaishi region, and at the end I put a couple of slides about these two places here, but Kamaishi and Miyako, you see different amplitudes, but large. Please notice this is 10 meters. Kamaishi is much larger, and there is a sort of a resonance there. Look at this very long period, pretty much monochromatic arrival that was here. And please notice that the period here, it's almost 30 minutes, so it's very long. If you multiply by 30 by 60, you get 1,000 of seconds here. And of course, the different maximum amplitudes and resonances here are caused by the, the local bathymetry. You can call it a sort of a side effect for these very long period waves. Okay, in this picture, you see the collection of other sites that have been modeled and compared with the recordings. And what this modeling is also allowing is, of course, doing a sort of a direct solution of a problem. So given a source, let's model it, and let's see what are the synthetic tsunami grams related to that. You see here now, you do understand what is this. That's a focal mechanism for a point source that is staying there. You know pretty much everything. But what you can do is also now to try a sort of an inverse problem. So you create a model of a source using the representation theorem, for example. You divide the fault into sub-events, you model them, and then you compare with data. And from this comparison, you try to get some parameters of a source that maybe in other kind of signals are not that evident. Now, let's think about it. And let me try to make a 1-minute pause as usual. What is it? Stop sharing. Okay. And just let me ask you one question. From the lecture about representation theorem, focal mechanism, and the Haskell model, I hope that you have understood that that theory can be used to invert for some source parameters, like duration of a process. Now, if you use time signals that are related to seismograms or accelerogram, you're using seismic waves. And the resolving power of a seismic wave is related to its wavelength. Now, also looking at some of the seismograms that I've shown to you during the lecture about seismometry, I hope that you get the message that the periods related to seismology can go from long periods, let's say 1,000, 100, 10 seconds, 1 second, and then to high frequency, relatively high frequency signals, 1 hertz, 10 hertz engineering seismology. So we have a huge set of wavelengths there. But if you consider an average seismic velocity of, I don't know, but of the order of kilometers per second, you do understand that the wavelengths that are related to seismology can go to some meters, very high frequency, okay, 10 hertz. You may have wavelengths of meters, tens of meters, hundreds of meters. Then you can go to the long period part, let's say 100 kilometers, 100 seconds, times some kilometers per second, very large wavelength. What I'm trying to say is that according to the signal that you're looking at, surface waves, body waves, high frequency body waves, you can get a message from the source that has different resolving powers because it's related to the wavelength. So acceleration is giving us beautiful details of a rupture, but it will be a very complicated signal. You have seen them, and you will see also in the last lecture. Going to long period surface waves, okay, you can get some other details of the source. Now, the tsunami waves are giving us a very long period of the source, very long, because they have 1,000 seconds and very large wavelengths. So the source, as seen from the tsunami waves point of view, is made by pixels that are very large compared to some of the tiny pixels that can be used using seismological data. Just to convince you, let me try to break everything and to open the first lecture that I was showing to you. Okay, let me order it by name. And in the intro, it's going to take some time because it's full of movies, and I was showing to you one of the pictures, and let me show it to you again. Okay, for example. So just a recap, we can use these two final lectures also as a recap. Let me share again my screen. For example, this was one of the pictures that I've shown to you at the beginning of the course. You see acceleration time series and displacement time series. Please get a feeling about the units. It could be centimeters, but here they are reaching 1 meter. In the other case, centimeters per second square. And you can compare them with gravity acceleration. So that is pretty much 0.4 g. Look at the different wiggles inside these signals here. Tiny wiggles, longer period wiggles. And we got here different information. For example, one piece of information that you can get from surface waves is this vision. It's just a model of the slip on the fault. This is one vision. Look at the pixels. The pixels here are related to the period of the waves. So let's say, okay, let's say that these are 600. Let's say that these pixels are made by 10 kilometers. Now, if you use other waveforms that are much longer, like the tsunami ones, the image that you can get is the following. And this was the message that I was trying to give to you. So you can do an inversion for a slip on the fault, also using tsunami signals. And the pixels that you get are, well, they are large. Why? Long period, very long period. And the part of the rupture that was more efficient in generating tsunami waves, actually, it's the first part here. So you see the high frequencies that have been released by the rupture to the north and to the south, actually they were not very efficient in generating tsunami. Why? Because it's a long period signal, very long period. And please do remember, and now I'm sorry to stop sharing again, but I want to have an interaction with you. Please do remember that the source spectrum is supposed to be flat when you go to zero frequency. So let me use this, if it is not going to collapse here. Whoa. Here you have M0. Here it is going as 1 over omega squared. So the flat part is going when you consider very long period, as I told you. Now, how much is long period? Well, on routine basis, surface waves, let's say 100 seconds. Please remember saturation of a mass at 20 seconds for earthquakes with magnitude larger than 8.2. So we have to go to longer if we want to appreciate the flat part. Okay, longer, 100. That's not enough for magnitude 9. Let's go longer. The three modes of the Earth. The paper that I hope you read by Stein and Ockel using S02, 54 minutes. And they were reaching the flat part for magnitude 9. Well, another long period signal is tsunami, because it's very long. So actually, the long period part of the radiation is, let's say, the most responsible for tsunami excitation. Question to you, it's a wake-up question. Do we have something longer that can be used? We already discussed it. Do you hear me? Oh, maybe you don't hear me.
Yes, we do. Bro.
Oh,
Yes.
thank you. So I'm waiting for an answer.
You're telling us that a type of event that we can use with longer period is where you're
Which kind of, my question is, do we have some signal coming from an earthquake that has a period longer than, let's say, hours?
Is the rupture, when it's occurring the rupture?
What do you mean by rupture?
When it's sleeping. When it's
Let's try to be a little bit more accurate. Let me open again my first lecture. What's happening here? Okay. And one of the first. Okay, let me share again. Okay. I hope you do recognize something that you have seen, okay, let's say 1 month ago. Are you with me?
Yes.
Yes. Okay, look at this
Yes,
signal.
yes.
That's a GPS, beautiful displacement. Look, these tiny wiggles here, beautiful. For a seismology, that's beautiful. Well, that's it. It's beginning to happen something here, and here, oh my God, we have a tilt. And this signal will never come back again because we have a near field. So if you stay near the source, you get the near field measurement, if you have a GPS, of course, and the pen of a seismogram is not going back to the equilibrium. It's not a transient like here. This information will stay there forever. Well, of course, at the next earthquake, it's going to create a staircase. But this piece of information is not a transient, it's static. So in principle, it has infinite period. So the answer, my friends, is blowing in the near field. So that's why the near field measurements, or what we can call co-seismic sleep, by Alessandra Borghi, for example, are a long, very long period information about an earthquake.
Okay.
Have I answered to my question?
Certo,
I hope
Yes,
so.
yes.
Okay, so I'm very good. I'm posing questions and trying to answer. Okay, please remember this, okay? Okay, let's go on, guys, because we have to proceed with tsunamis here. Okay, two final movies here that I've already shown to you, that are giving us a feeling about the time. 40 minutes here. So it's much slower, okay? And if you take the vision of a pan-Pacific message here, the arrival times are getting very, very long here. And you have to wait, let's say 12, 18 hours for the tsunami waves to reach the other side of the ocean, and almost 24 hours to reach, for example, the Chilean coasts. Now, this movie here is very important. Why? Because it's telling us some important features of the tsunami physics and hazard. First, let me go back. Now, we have seen, look at the time on the top right. We have seen that in 40 minutes, the tsunami waves are reaching the Japanese coasts. But in some more time, they are reaching the buoys that are deployed in, the first ones that are deployed in the Pacific Ocean on the other side of the rupture. And in some time, they are reaching them, the first, then the second, and so on. Now, you have to know one thing here, that actually what you see in the bottom panel is the comparison between pre-computed time series and recordings. Of course, they are not perfectly matching, but in terms of maximum height and maximum arrival height, they are very good. Now, these time series have been computed by NOAA, that is the US agency that is devoted to tsunami hazard in cooperation with Japan and with many other countries like Australia, like Chile, for the Pacific tsunami warning, because after they collected the information about a magnitude, a large magnitude, at the beginning it was 8, then 8.5, then 9, they began to use this information and the location of the earthquake to use pre-computed time series to assemble them, like in the representation theorem approach. You remember the sum over the sub sources, blah, blah, okay? To estimate the time series after, let's say, you see, this is 1 hour. So in tens of minutes, they assembled this tsunami time series. They validated with available observation when possible. And then after that, they can issue a sort of a tsunami warning, if necessary, for the other coasts on the Pacific Ocean, facing on the Pacific Ocean. Now, the Pacific is very important, but it's very large. And actually, it was the place where the first idea of a tsunami warning center started when, well, in 1960, after the Valdivia earthquake, the strongest earthquake in human history, according to the magnitude that is estimated to be 9.5, that occurred on the Chilean coasts here. And the day after, so you have to imagine to reverse this animation, the day after killed tens of Japanese fishermen that they were not waiting for this wave. And also they killed other people on the small islands in the Pacific Ocean. So, for example, Japan and US, they decided to cooperate and to build a tsunami warning center, TWC. And you can do that in the Pacific. Why? Well, because there are important countries that are high-tech countries, rich countries, whatever, and you have very long times, because here it's 24 hours. So it's not easy, but it has been becoming easy to build this TWC in the Pacific, because high technology, let's say, funds and whatever, and long times. But when the Sumatra, December 26, 2004, occurred in the ocean, in the Indian Ocean, there were no buoys at the time. Now there are. And so that tsunami was a sort of a very tragic surprise for most of the people there, people over there in many other parts of the ocean, because tsunamis are slow, long period, but they can propagate very efficiently because the queue of water, if you want, is very high. So dissipation is happening there, but mostly in the interaction with the bottom and due to spreading, because the queue of water is relatively high. So it's really a transoceanic phenomenon here. Okay, now we have seen all these beautiful fashions, beautiful and tragically beautiful features of a tsunami, especially for the Japanese coast. Now let's spend 10 minutes in trying to understand what are its physics. Well, they are relatively simple. And if you want to use some high school physics, the main message is, okay, if we have a seismic event that is perturbing the equilibrium of a fluid, okay, like for example, this is not always the case, but it's easy to imagine that we have, for example, like a thrust event. So you're pushing the bottom of the sea and you're giving potential energy there. Which kind of potential energy? Well, for a fluid, for a liquid, the most important potential energy that could act as a restoring force is gravity. So you're giving gravitational potential energy that is going to be converted into kinetic energy, and gravity waves will depart. Now, if you want to make some very, let's say, how to say, pencil and paper computations, just to have a feeling, well, we can use the Gutenberg and Richter relation connecting energy and magnitude. You can go 2 lectures back, and you have an estimate of the energy involved here. You can put a 9, you get a value in joules, for example. What about the tsunami energy? Well, let's compute the gravitational energy. L could be the length of a fault. Lambda could be the width of the surface interested by this uplifting of the bottom. Rho g is, of course, related to the gravitational energy, and delta H is the average height there. Okay, if you put the numbers related to a magnitude 9, what you get immediately is that the total energy involved, remember also the seismic efficiency, there actually is much larger than, at least 2 orders of magnitude, than the energy that can be converted in gravity waves. By the way, for a large earthquake like magnitude 9, that energy is still huge. And we will see how this energy actually can be converted during the tsunami propagation. By the way, if you compare, for example, the wavelength that you're getting there, let's say that you're perturbing with this wavelength here, that is the length of the area for a magnitude 9, and if you compare it to the height of a fluid, well, the wavelength is much larger, much, much larger. Oh, sorry, before I had been saying deep water. I'm very sorry, actually it's shallow water. Discussion in a few minutes here. So wavelength is much larger than the height of a fluid, and this in fluid dynamics, it's called shallow water condition. What else? Well, the thickness of the fluid compared to the amplitude that is starting to propagate here, actually near the source, it could be 1 or 2 meters. You could say 1 or 2 meters, that's nothing. Well, it's maybe nothing, so it's a tiny amplitude, but actually it has a giant wavelength. So the energy that is involved in this motion at the beginning is huge. But the tiny amplitude at the beginning was also the origin of the name tsunami in Japanese, that means a wave that is in the harbor. Because actually in open ocean, with such a long period and tiny, relatively tiny amplitude, maybe you don't notice it, but you notice it when it's arriving to the coast. And that is mainly due to what is called shoaling. So the amplification due to the thinning of the water layer. A little bit more detail is coming in the next slides. So to sum up tsunami physics, you can say that tsunami is a shallow water due to this, gravity wave due to this, we're in a liquid, with great wavelength and tiny amplitude. So this is maybe a too simplistic statement, but it's summarizing tsunami physics. Okay, sorry, let me take a note that I want to discuss later, that I just noticed here. So tiny amplitude. Is it the end of tsunami physics? No, it's not. And you can take different approaches to model and to study tsunamis. The typical one is coming from fluid dynamics. You could say, of course, it's a gravity wave. Yep. So if you go back to your fluid dynamic courses, you can study maybe some Euler equations. You apply the boundary conditions. And the boundary condition is that a typical liquid in a gravity field is creating a free surface. Okay, that's the equilibrium condition. So you can imagine to put some water in a glass and to shake it. Of course, it's going to move, trying to react due to the gravity field. Okay, then you can take a condition at the bottom that is giving us a thickness. And what you get from typically Euler equations, a rotational flow, whatever, very simple, you get what is called the dispersion relation for incompressible irrotational small amplitude gravity. Main simplification, and that's it. Now, which quantities do we have here? Well, the restoring force, of course, G. K, with number. H, the thickness of the fluid. Omega, of course, 2 pi times the frequency. And usually, this dispersion is studied in 2 branches. The first branch, deep water. What does it mean? Not that it is absolutely deep. No, but H is much larger than wavelength. So maybe you can study tiny waves also in a glass. Capillary waves in a glass, you're in deep water. And if KH is going to infinite here, well, the hyperbolic tangent is going to 1. And this is becoming the relation for deep water waves. On the other side, if the wavelength is much larger than H, and H could be Mariana's Trench, but your wavelength is 100 kilometers, this is going to 0. And so this is going to KH. And here you're facing this. Now, what is the difference between deep water and shallow water? Well, in terms of velocity, because please remember that omega over K is velocity, is that here you have dispersion and you have phase velocity that depends on lambda. Groove velocity that can be approximated to 1/2 of the phase velocity, while here you have no dispersion and you got the expression that I was writing before. I was terribly wrong before. I was saying to you deep water, no, it's shallow water. Please remember that these adjectives here are expressing relative amplitudes. So you can be in deep water in a glass of water, and you can be shallow in the deep ocean. Everything is related to the wavelength. Okay, now what about tsunami? And what is coming now, that was my note just to join this, is a sort of a summary that is coming from a beautiful piece of paper. Actually, it's a sort of a piece of an encyclopedia written by Stephen Ward, and he visited ICTP some years ago. And so you can easily find. Let me check if I have left that on the Moodle this year. I guess so. So let me wait a second. Let's discuss this slide and then I will check, because this is the most important for today. Now, what do we have here? Okay, we can call this eigenvalues and eigenfunctions problem. Now, it's a sophisticated jargon just to discuss phase and groove velocities as a function of period. Also, surface waves, seismic surface waves like Rayleigh waves and love waves, they can be described by eigenvalues, phase velocity, and eigenfunction, the profiles of the modes. Okay, what about gravity waves? Okay, here you see the plots of the previous expressions for different ocean heights. Okay, when you go to very long period, look here, you have flat lines, no dispersion. Now, long period, what does it mean? That wavelength is very, very large. Shallow water, then the period is beginning to decrease. You can go to, let's say, 100. Wavelength is 10. And now it's becoming to be comparable with the ocean depth. And actually, now you see that the deep water is beginning to appear here. If you go to beach waves, and usually they are gravity waves, but are excited usually from the top by wind, for example. And so the excitation there is very efficient on the top, and it's causing just tiny wavelengths. You see, well, if you're in open ocean and you see 100 meters gravity wave caused by some streams or giant winds there, okay, you can say, oh, wow, it's 10 meters, it's not a tiny wave. No, but it has a relatively short wavelength. You see 100 meters, well, it's not short, but it's tiny compared to these ones. And here you're totally in the deep water regime. And if you give a look to the eigenfunctions, and if you travel from long period, the tsunami window, so please remember 1,000 seconds, 100 kilometers, and a typical velocity of 200 meters per second. Okay, if you go there, look at how the motion is done. You have an ellipse, a typical ellipse of a gravity wave, and actually the vertical component is decreasing with depth. And then if you go to very short periods here, you have a typical and beautiful vision of deep water waves, and you have a circle whose radius is decaying very rapidly with depth. And here you get the very big difference about gravity waves, shallow water, deep water, and the different excitations, because this one can be excited very efficiently from the bottom. This one can be excited very efficiently from the top. Now, before going to the last part of tsunami physics, now I have to run because we're getting short of time. Let me ask you, I assume that most of you attended the fluid dynamics course. Yes. Is that?
Yes, yes.
Okay, for diploma guys, yes. What about you, Maria Aurora? I think so. I cannot hear you, but okay. Is it a yes?
Well, I have seen some physics, some course physics, basics, physics where we try some fluid dynamics. Not a proper course called it fluid dynamics, but in previous courses I have seen some science, yes.
Okay, my message here is, if you consider the equations that you discuss in basic or advanced fluid dynamics, like Navier-Stokes equations, like Euler equations, well, you can use them to model tsunamis. But let me tell you one word, because they are gravity waves, shallow water gravity waves. And usually the codes, yes, just let me conclude this. Okay. That was my note. Because usually the approach for tsunami modeling is based on fluid dynamic equations, fluid dynamic boundary conditions, so the free surface, the beautiful finite elements or finite differences computation, very detailed, very nice. The problem with them is the boundary condition in the bottom, because in fluid dynamics, the bottom is supposed to be rigid. Okay, that's a boundary condition. Now, how to model the source that is here? Well, that's the problem with that approach that is called uncoupled approach. This is what I was trying to tell you. And the source is included in the computation as initial condition of the shaking of the bottom. So you have to map the slip on the fault as a perturbation of the bottom and then to start the modeling. There is another approach that has been proposed by Stephen Ward and others, ourselves included, that is using actually a model approach. I will not enter into any detail here, but let me tell you, it cannot treat beautiful bathymetry like numerical approaches, because it's an analytical approach. But on the other side, it's very easy to include the seismic source in the computation with the same fashion that we have studied discussing the representation theorem. This was my message to you. And now, Maria, will leave to you the floor for if you have a question, but let me check if I have left the Stephen Ward paper on your...
It is fine, Professor.
Okay, please tell me.
No, it's fine. I mean, just a comment regarding the fact that fluid dynamics, I mean, I saw it a long time ago. That's it.
Okay.
Those concepts.
Sorry.
Yeah.
No, that's fine. Well, the summary of that is in my slide. So that slide is coming from a typical fluid dynamics course, and that is the approach that is traditionally used. Okay, On your Moodle website, actually, seismic hazard is coming before the tsunami hazard, but we will use them as a sort of a commutative product. I've left there the PDF of Stephen Ward that is also, if he is a modal approach, how to say, player, actually here in this paper, you have pretty much everything. Let me, okay, now I'm not sharing the screen, but here you are. So in the Moodle website, I uploaded this, okay? And it's containing much more than what I was discussing there. But here you see this picture and that expression as before. And with many other examples of application. And well, you should remember this, maybe. Many modeling, focal mechanisms, and whatever. So this is containing much more than what we are discussing here. Just if you want to go deeper along that way, you have the material on the Moodle website, just here, okay? So these are the slides that we are discussing, and this is the additional material that you can read. So you can call this as your homework, not only for Friday, but also for the near future, if you want to deepen the matter of tsunamis. Just to relax you, let me tell you that at the exam, I will just ask, as usual, what we are discussing here. Nothing more, okay? And usually I'm asking you the logic. Well, usually it's only the logic. Well, at least the logic. Okay, let's go and see some other animations here, because there is one additional feature that is important to understand tsunamis. And the first one, okay, it's already with us. It's the dispersion, shallow water waves, deep water waves. Look, long periods are faster. They arrive first. Shorter periods, deep water, are slower, and they are arriving here. What's going to happen next? Well, this. And this is called the shoaling effect. You can demonstrate it just by using with simple tools. You can call it the Green's function of fluid dynamics. It's the same Green, but with not the Green's function, but the Green's expression, Green's law of fluid dynamics. Well, what's going to happen there? Well, when the fluid thickness, the liquid thickness, the ocean thickness is getting thinner and thinner, so when you're approaching the coast, well, actually, the wave is getting slower. Remember, on average, square root of g times h. So you have some consequences there, basic ones. If it is getting slower, all the wave train is getting slower. And now the waves that are arriving from your back are going to interfere, and the amplitude is going to increase. So what was 1 or 2 meters in open ocean, now, according to the bathymetry, to the local bathymetry, now can rise with amplification, and can go up to 10 meters. And then in the final part of a tsunami travel, okay, now the amplitude of a wave is getting larger than the thickness of a fluid. And that's the nonlinear part of its propagation. And to do that, you have no way if not to use numerical computations, if you want to make simulations, where you do study the interaction between the solid, the barriers, whatever, and the fluid. And so in the final part, you have the breaking of a wave. Remember that breaking of a wave, like in surf, okay, that's the nonlinear part of the wave field, because amplitude is getting larger, the wave is going to break. Why? Because larger amplitudes are faster than the other ones, so you create the beautiful logo of, for the people that is going to surf the waves, you can surf that. But in open ocean, no. But this is the final message about physics. Since you're getting to slower media, the wave field at the beginning is going to stop, but on the back, something else is arriving. So this is called shoaling. There is another consequence of the fluid getting thinner, and that's very familiar with all of us. Because if it is getting slower, due to the Snell's law, the ray, that is the direction perpendicular to the wavefront, whatever the direction of the waves compared to the seashore, well, the normal, the ray is getting parallel to the normal. Why? For Snell's law. Because if velocity is getting slower, well, the refraction angle is getting slower, and so the wave will arrive at the end of the story parallel to the coastline. But what is very important here is the amplification due to the shoaling effect. Okay, now what we're going to see here is a series of animations. I will be very quick. Let me check that it is working, sorry. I checked a few months ago, I think it's still there. Come on, Steve. Yes, okay, so you can explore many things done by Steve Ward. I will not, you can look at them, because Stephen Ward with his beautiful theory was amused also to generate some modeling, not only for mega earthquakes, and not only for mega earthquakes that occurred in reality, but also that they may occur. So here you can see a sort of a tsunami propagation from a magnitude 7 in front of the New York City. This is an animation, I will not lose my time, but just to show to you that a tsunami can be generated also by an impact from above. It's not earthquake induced, but it can be caused by, like wind, by, for example, an asteroid. In some parts of the Adriatic coast, you may have some, let's say, dangerous tsunami caused by large meteorological phenomena, like very important storms, especially in front of the split coast in the middle of Adriatic. They are called meteo tsunamis, but they're not that large as the giant ones, of course. You can have tsunamis generated by landslides, and that's important if you're going to study tsunami hazard. It is related to the last slides that we are going to see today, because, for example, maybe an earthquake is not causing directly a tsunami, but it may cause a landslide, also a submarine landslide, and of course, you are perturbing the equilibrium of a fluid. And if you have a giant landslide, like this one that he was modeling in Lituya Bay, that is in Alaska, you may have giant tsunamis that can be channeled in some bays there. And the final one, okay, let's play this one because it's referring to an historical event that is narrated by, like the Santorini volcano explosion. And it was, let's see if it is working. Yes, okay. And so not only earthquakes, not only asteroids, but also explosion like large ones. So he was simulating this, and he was getting from this equivalent source very large heights along the, especially along the Minoan, of course. There was, at a given time, there were some labels, but here they are not appearing, so I'm sorry for that. But okay, you may have a reference here. There were supposed to be some labels. Here, he was getting tens of meters, really tens of meters. So another simple message to take home, that tsunami waves has gravity waves that can be generated by asteroid impacts, let's hope not, landslides, and explosions. And for example, you may have some volcanic explosions. One occurred in the Stromboli Island here in Italy a few years ago. A volcanic earthquake and explosion caused a small landslide that caused a small tsunami. They're called local tsunamis. So they are not propagating along an ocean or a sea, but they can cause some important heights near the island. They are called local tsunamis, and they can be induced by landslides. Now, a final word, it will be very quick, about something that is coupling the tsunami also with other fluid dynamic branches, like physics of the atmosphere, because after 2004, people began to investigate with GPS an important features that was studied in theory since the 60s. And it's called the coupling. Of what? Well, you can imagine a full coupling between the solid Earth, the earthquake, part of a fluid Earth, the ocean, so tsunami is generated, another fluid part of the Earth, the atmosphere, because the wave, the tsunami wave field, is also causing pressure and gravity waves in the atmosphere. They are very tiny. You cannot listen to them. But this message is going to be propagated as what is called traveling ionospheric disturbance up to the space. Because here you have the tsunami wave, you are creating energy, some tiny energy in the atmosphere, and when it's reaching the ionosphere, this is causing some electronic currents that are amplified, and they can be felt by satellites, for example, the satellites of GPS communications. So it's noise for them. The theory has been developed since the 60s, but the first evidences had been found around 2004, 2005. And that's why I'm here showing to you this nice video that is showing that tsunami generated gravity currents in the ionosphere. And you see this wave passage here. Oh, sorry, let me show it again. These are these tiny signals, but actually they become very strong in the ionosphere, and the satellites can feel it. Let me show it. Oops, sorry, this was for the Japanese, and this was the tsunami and some surface waves seen via ionosphere using GPS signals. So one of the final messages before going to discuss what can be called the other problem is the following. Tsunami is a gravity wave, tiny amplitude in open ocean, then we have shoaling, okay, gravity, tiny, long period, very large wavelength. But it's also coupling pretty much all the geospheres, the solid, the liquid, the gas, and the deep atmosphere, or if you prefer, the ionosphere. And GPS is a tool to study it. So another simple message to take home here. Now the final slides are about a different problem, because we can use, with the different approaches of tsunami physics, different research lines. For example, the first one can be used also to monitor, like in a tsunami warning center or system, and you can do some modeling, for example, just to understand which one is the best place to put the buoys and so on. So it can help tsunami monitoring networks. The second, and you have seen it, it can be used to also as a powerful tool to give operational forecasts and warnings, because you can decide an evacuation in an island in the Pacific based on tsunami physics research. Of course, you can also study the source, the seismic source with inversion. But maybe the most important one is to deal in the prediction of future tsunami impacts. And this is leading us to the final topic of this course, of today and of this course, that is sort of the thinking time about the problem of hazard that we're going to define in the next lecture. For today, let me just show to you some features related to the tsunami. So we've seen that we can use tsunami physics to build a tsunami forecast model. So what you can do is generate, before an earthquake occurs, a database of pre-computed scenarios. So you take all the potential sources, you put there a sort of a unitary amplitude, and you compute, if you want, the Green's function in the ocean. Okay. Then you get information about an event, a place, and the magnitude, and you use these pre-computed scenarios, you assemble them, and then you can predict, on average, what is the most important arrival time, what is the maximum height, and if you want, you can use this to do a subsequent simulation process, dealing with nonlinear codes, with the interaction between the fluid and the solid part, and you can do some inundation modeling and to predict inundation maps. You can do this for an event that occurred or for an event that is going to occur in the future. And this is leading to the concept of hazard in general. So to produce a sort of a scenario-based approach where you can say, okay, if an earthquake of that magnitude occurs or had occurred, then the predicted maximum height will be, or head would be, and so on. The concept of hazard that we are going to define in the next lecture. And two messages to take home. One, I was watching on this movie, I hope it's going to work, because, okay, this is a very nice simulation related to December 26, 2004. And actually, after this event, all the news, the media started to talk about tsunamis. So the first message is, okay, nature of a subduction zone like in the Pacific here can provide us with natural phenomena that can occur in many places in the world, but the only and most studied place was the Pacific. In the Indian Ocean, actually, the hazard, we can call the hazard, the nature, was providing us events that could be as well as dangerous, 9.2. What is the difference between these two? Well, now we can think in terms of what we're going to discuss on the next lecture, what we can call vulnerability, and another factor that is called exposure. And vulnerability in the ocean, in the Indian Ocean, and exposure, let's think about the Indonesian coast, and especially to the Indian coast. There are some nuclear power plants there. I visited there, they're just on the coast. And so exposure and vulnerability there, they were very large because there were no countermeasures at that time. In 10 years, many things changed here. So just to tell you that hazard is nature decided in some way, but we can assess it. Vulnerability is part of it, well, most of it is man decided, and we can diminish it. And this is the message also that I want you to take home also for the next lecture. And one of the ways to diminish vulnerability in Japan before 2011 was to build many things, a new culture, because Japanese pupils are trained to react to earthquakes and tsunamis since they were childs in the school, whatever, prepared. Second, many physical, seismological observation. Third, many engineering efforts. For example, in Achinohe, this is an example of a seagate. This is another example of a seagate. It's impressive. In any other part of the world, we could find such kind of things. But look at the heights. Okay, other impressive seawalls. This was Kamaishi, the deepest breakwater. So the feeling was that before 2011, the Japanese country, the Japanese society was, and actually it was, very ready to this kind of events. And actually the ground motion, we will see on the next lecture, caused some damage, but it was a magnitude 9, but let's say relatively low damage. But what about the tsunami? Preparedness was at top, with science, with engineering, with whatever. But then what occurred in reality is that most of the seawalls, also impressive ones, like this 2.4 kilometers long tsunami wall in Miyako, it was 6 meters for 2 kilometers. Can you imagine? I cannot imagine. But actually, it was totally destroyed. Well, there was another tsunami wall, Fudai, sorry, it's Fudai, not Fundai, near to Miyako, that actually it was much larger, much higher, and it resisted, and it saved that village. Now, the final slides, just to make us think about this phenomenon, because actually the seawall at Fudai, it was much higher than the other one because the mayor decided to build it following the messages coming from the past, like, for example, the 1896 Meiji event. So he was fighting to make it higher. And it was not easy because you can imagine that it's much more expensive. And if no tsunami occurred, no one had complained. Well, maybe had complained why we are spending so much money, much amount of money for something that maybe it's not useful. And that's one of the problems when you decide to decrease vulnerability, because to decrease vulnerability, cost is a key factor, especially from a political and social point of view, not scientific. By the way, this seawall that was built in 1967 saved that village. And actually, you see the differences between these two tiny villages here, or well, villages, actually they're mostly important cities and for fishermen at the time, but one is being totally destroyed, the other one not. And actually, one of the messages is coming from the past was, for example, the tsunami stone, that it's called tsunami seki, and it was placed there as a warning for future generation after the Meiji event to say, please don't build after this because the tsunami reached this height. So, okay, we have still some messages from the past that can be learned from this. And actually, we have to learn from nature also what to do, because, okay, I will spend 1 minute about this map here because I'm using it to discuss about hazard in advanced course, but I want to show it to you because it's impressive. This is a beautiful map released by a Japanese agency that is devoted, you can see here. It's the headquarters of the Earthquake Research Promotion. It's released every year, and it's based on a time scale of 30 years. This was released on January 1st, 2008. And you see it's going to break the subduction zone in many tiny little beautiful places with magnitude and probability to occur in 30 years. And if you see some of them, they're impressive, 90%, 99%, well, 20%, 87%, okay, 8.1, 7.5. So they were ready to a magnitude 8 or more, maybe, also 8.2. And so the defenses were ready also for, let's say, up to 10 meters for a giant tsunami caused by a magnitude 8. But then what nature decided to happen was this, because this map here has been released on January 1st, 2011, and what occurred in practice, in nature, is that all these tiny pieces of events collected together in a magnitude 9. So you see, this is the area of the Tohoku event of March 2011, and it's including this. So the final answer, well, not the answer, the final slide that I want to show to you and I hope it's going to make us think also for the next lecture, is the following. And this is coming from Stein and Ockel, and you have the paper there. And okay, you can try to understand what's going to occur in nature, not only for scientific reasons, but also for hazard studies. And so if you have a magnitude 8, it's here it seems tiny, but can you imagine a magnitude 8 in front of Mediterranean coast, or magnitude 8 in other countries? Well, it's going to be a very scaring event, but not for Japan. Well, the average slip for magnitude 8 is 5 meters. And if you want to use a sort of a rule of thumb, the run-up that you can have from a 5 meters slip on a fault, let's say that you're going to have 5 meters or less in open ocean, but you can have, let's say, twice of that as a run-up, so 10 meters. And that was fine with the available defenses. But actually, what nature decided was a magnitude 9. Now the slip is, please remember the lecture about magnitude. Now we have 10 meters, and 10 meters become 20 meters as a run-up. And that was the surprise, the bad surprise that occurred in Japan. I don't want to show to you this. These are too technical, and because they are based on deterministic and probabilistic hazard assessment. But the message here for the last 3 is that Japan spent more than 20 years trying, on tsunami hazard assessment, with all the available methods, advanced, at the frontier, in jargon, probabilistic and deterministic, whatever. And look, they were also going to refine these approaches. Actually, these slides are coming from a meeting that occurred in Niigata in November, just a few months before the event. And well, okay, you see, this is Fukushima Daiichi nuclear power plant. And the results of a study a few months before the event was that you see, operating level and the maximum tsunami 8 weighted there from all the methods was 5.7. And so the assessor confirmed the safety of the nuclear power plants. Okay. Well, you know what a few months occurred. And actually the tsunami height at Fukushima was in some places also of 12 meters. So my final message for today is that, let me stop sharing here. Okay, what we have done today was a small, short travel through tsunami physics, about its excitation, about its definition, and about some possible ancillary studies that actually are very important in terms of hazard and risk. For today, we discuss tsunami hazard and risk. On the next and final lecture, we're going to recap some what we discussed during this course with a view about seismic hazard and risk. And I will show to you what are the basics of this. We will see also we will start from some definitions, but the basic definition, also if it is a little bit too simple, is that it is the product, risk is the product between hazard and vulnerability. So in principle, if you zero vulnerability, you got no risk, also if you have a very large hazard. The point is, as in the event of March 2011, is that to decrease vulnerability is based also on hazard assessment. And as you have seen, they were ready for a magnitude 8.2. I think in no place in the world people is ready for an 8.2, but they were, but nature decided for a magnitude 9. So still work has to be done. Okay, that's the end for today. If you want to go deeper in tsunami stuff, you have plenty of material in the net, but I like that paper by Steve Ward. And okay, we will meet again on Friday to close the course, trying to use again the Toku event, and not only that event, but just to apply it to the concept of seismic hazard. Okay?
Yeah, okay.
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 Okay, okay.
Okay, my friends, good afternoon, and let's meet on Friday.
Same for you, Professor. Thank you.
Thank you.